Hey everybody, welcome back to HPC Tech Shorts, where every week we take you to the water cooler here in HPC Engineering and we talk to some of the engineers, the scientists and the architects who are making AWS the best place to do your HPC in the cloud. Last couple of weeks ago, we spoke to Austin Cherian in Singapore on our development team about some of the work that he'd been doing with GROMACS and from a CPU point of view. And he'd written a blog post, which we'll link to in the show notes, and I'll put a link in there to the last talk. But we were talking about, in particular, different CPU architectures and how they contributed to GROMACS performance. So fast forward to this week, we're actually sort of bringing in the concept of GPUs now and talking about how GPUs track with GROMACS and how that compares to the different CPU platforms as well. And more to the point, examining how all of these things scale and how all of them impact performance and, across the board for different models, large molecules and small molecules, and large systems and small systems. So anyway, with that, let me just say, I'm very happy to be joined this week by our good friend Carsten. Hey, Carsten.
Hi, Brennan.
Carsten is a researcher and developer of scientific software at the Max Planck Institute for Biophysical Chemistry in Göttingen. Did I get it right?
Göttingen, yeah, perfect.
Göttingen. Okay, I'm getting better in Germany, and he's one of the significant contributors to GROMACS. Also with me is Christian Neek from our Dev Relations team in HPC Engineering in Berlin. And of course, one of the original instigators of this discussion, Austin Cherian from Dev Relations in Singapore. So thank you, everybody. Lots to talk about, so we'll get started quickly. Carsten, you're a member of the club of people that measure your computational progress in nanoseconds of results, nanoseconds of simulation time per day of wall clock time. You need a lot of compute, right?
Yeah. So basically, we're doing biomolecular simulations in atomic detail. And so the systems that we are looking at would have at least, 10,000 atoms to, 10 million atoms or even more. So even a small protein in a water droplet also would make a few tens of thousands of atoms. And we are looking at we try to understand these and we try to understand the biological mechanisms behind them. So, for example, channels that that permeate ions in the cells, right? And they open up and they close. And so just a single opening up and closing could take a microsecond to a millisecond, depending on the channel that we are looking at. And for numerical reasons, the time steps that we do can only be at most a few femtoseconds long. So we need millions and millions and millions of time steps to just reach nanoseconds or hundreds of nanoseconds, and we need, let's say, a microsecond or so to arrive at something that is meaningful. So yes, we are really looking for the fastest speed that we can get.
This is the canonical HPC workload. It really is.
Yeah.
All right. So let me see. So let's start with decomposition, because I think this is really where it all begins, right?
Yeah, so we're using the GROMACS MD software to do our simulations, and nowadays we like to make use of as much compute power as we can get to speed up the simulations, and GROMACS does this by chopping up the whole system into a bunch of domains, and we could then have each domain computed on a separate instance or node or MPI rank, for example. So here you would see an example of such a system. So the stuff in the middle, this light blue stuff, that would be some kind of a protein, and around that in red and white, that would just be water. This would all be, this is just one image out of a periodic cell, out of many of such images. And here you see such a decomposition. You see 6 domains in the X direction, 4 domains in the Y direction, and 3 domains in the Z direction. And this is one possibility to compute that system, for example, on 72 ranks. So you could have that computed on 72 instances or on 72 MPI ranks, or even offload that to 72 GPUs, for example.
Right. And I think what we can see here as well is that water is not some solid thing, right? There's a lot of void in water as well. Like this is a little red and white dots, right?
Well, yeah, I mean, of course, so these atoms interact via interaction potentials. They have van der Waals parameters and they have Coulomb attraction and repulsion. And so this is just our picture of how we look at that. So, I mean, there is no real void in the system, but that's just a matter of how you look at it, right? And maybe, so going on in that decomposition and how to use compute time wisely. So we could then GROMACS even goes on, and so these domains are not operated on by a single thread or so. You can have multiple threads, multiple OpenMP threads operating on each of those domains. And then you can easily see that if you have an instance with lots of cores or lots of hardware threads, that you have many different possibilities of how you could decompose your system. And each of these possibilities will give you a different performance. And these performances can be quite different. Yeah, and so our simulations usually run for at least for days, sometimes for weeks, sometimes for months. So it really matters to get the most performance out of the instance, right? We don't want to waste 30% performance. Yeah, we want to be we want to finish 30% faster. That's what we want to do with the performance.
No, you want to simulate a 30% harder solution. That's what you want to do. We know these people. I've met your clients before.
Yeah, right.
So maybe show us some numbers. Because I think it's probably worth just getting some dimensions around this so that we.
Maybe here's
I think for the uninitiated, it's good to understand. What sort of scale are we talking about here in terms of time and memory and threads and so forth.
Right. So here would be an example. I mean, I know tables are not so really nice, but let's try to digest this one anyway. So this would be a C5 24XL instance with 96 vCPUs, and we have 2 different systems that we can run on. Maybe we can just quickly look at the systems here. So these are 2 benchmark systems that we use. So the upper one is a membrane channel. So this is 81,000 atoms large. So we have a lipid membrane, which is something like a cell wall, and a tetramer. So this is a water channel. And the other systems is a larger system. So this is a ribosome. This is a factory in the cell that makes the proteins, and this would be about 2 million atoms in size, the whole system.
Right.
And now we did run benchmarks with different decompositions. And if we just look at the C5 24XL instance here, then we see here's the membrane, the smaller system performance that we get. Here's the ribosome performance that we get, and maybe let's just look at the optimums. The optimum would be for a decomposition of 48 MPI ranks with 2 OpenMP threads each. So here we would get a performance of slightly more than 100 nanoseconds a day. But we could easily, with wrong settings, we could easily lose 20% here, right? And we don't want to do that. And that then also has implications for the price performance ratio that we get, right? So,
and that's what's the expensive thing there? That's what's going wrong in that scenario at a very high level. I mean, is it massive numbers of memory, unnecessary memory copies? Is it pushing data across a network that otherwise shouldn't be pushed across a network?
MD is not that memory hungry, so it's probably not memory. It's more that you have to the more MPI ranks you have, I mean, these maps one-to-one to domains in the domain decomposition, and you always have to communicate some domain overlap, right? So if you want to compute all the forces on your local domain, you have to communicate a boundary layer to the next domain to get where the atoms are there. Otherwise, you can't compute the whole forces on your local domain. And that, at some point, if you distribute that to more and more processes, at some point you are just communicating stuff around and you're not calculating enough stuff.
Yeah, that makes sense.
Yeah, I guess you're basically losing time in the Halo calculations.
Right, exactly.
Halo interactions rather than the actual calculations, right? And
exactly.
I think the optimal is when you have the right number of MPI and OpenMP threads, so it's always optimal.
Yeah.
But also one more aspect, Carsten, is these would differ for different systems, right? So maybe can you just give a quick on that?
So, I mean, on top, so if you have larger systems, of course, you can go to more domains. The halos are relatively smaller there. But on top of that, you also have load balancing issues, right? So some interactions are more costly than others. And you can imagine that maybe water interaction has a different compute intensity than, for example, lipid interactions or so, depending on how much interactions are defined there. And so that means the more domains you have, the more imbalance you will also assemble there. And this also adds to the performance loss that you can get. Although there is an automatic load balancing implemented in GROMACS, but you cannot, if the domains get very, very small, it reaches its boundaries of what it can do at some point.
Got it.
All right.
So in layman's terms, that's like the grid that we saw, right? It depends on how much is going on in each individual cell and how much you can balance the grid across the object that you are looking at, right?
Exactly. So here, for example, within the protein, you would probably have a different compute intensity than if you would compute just water.
Yeah.
Right. That makes sense. All right. Let's go. Let's look at your scary diagram.
Oh yeah, this one.
I think that this does a really great job, and also simultaneously a completely baffling job of summarizing the results. So walk us through it, because I think there's some good stuff in here.
Okay, so so this summarizes our benchmark results for these exemplary systems here, but it would also be valid for any MD system that you would try to run on these instances. So on the left axis, we see the GROMACS performance in nanoseconds per day. And on the x-axis, we see the relative costs. So this would be something like the hourly costs for the on-demand instances, or if we would run that in parallel on multiple instances, this would just be the sum of all the instances taken together. And in the upper part, we see these circles. So these are benchmarks for the smaller system. We see the open circles. These are just for CPU instances, and the closed or the filled circles are for GPU instances. And the lower, the stars, are for the larger system. So we get higher performance for smaller systems, right?
Yeah.
And so maybe maybe I should also say that. So now from the table that we just looked at, we're not looking at all the results from the table, but we're just displaying the optimal one in this plot. So we will always look at the maximal performance that you can get on these instances, to keep it a little bit simpler here. And for me, the main, or one of the main messages from this plot here is that GPU instances generally, so the filled symbols, will give you a way higher performance than CPU instances on average. And another feature of the plot is hidden in these gray inclined lines here, because these are lines of equal performance to price ratio. Yeah, that means if you have benchmarks or if you have dots that are on one of these lines, they they will have a different performance and a different price, but the price-performance ratio will be exactly identical. And if you move from one line to the next line, there's a factor of 2 between. So this is quite large differences, right? That means for our simulations, to make the best use of the compute time that we get, we want to be in the upper left region of this diagram, because there we are fast and there it is cheap, right? And these instances to choose.
Do you mind if I put this in layman's terms again? Like, if you export videos with iCloud or iMovie, sorry, if you have a powerful machine, you can export an hour of video in maybe 5 minutes. If you have a small machine, you can export a video in 10 minutes. So this will be 2 times the performance, and you need to balance it with the cost of the machine, right? And this nanoseconds per day is exactly this, right? How much simulation time can I get from 1 day of running one of those machines? Right?
Exactly. Only that we are talking about 1 week versus 2 weeks of compute time, right?
Yeah.
So it really matters.
That's the thing. I mean, if time is against you, and I can think of a lot of applications or environments where time matters a lot more than money, right? If you're let's say if you're doing something that's contributing to, say, a COVID vaccine right now, I think most of the world, 7 billion people, would shout in unison that time is more important than money for that problem. And so obviously there's going to be lots of shades of grey in the middle. But I think what this says to me is, I mean, very clearly, we can get we can scale the performance to whatever we need to, but obviously scale and speed comes at a cost. But there's some really big differences in terms of price performance. If you're on the price performance end of the spectrum, where time is not against you, but getting a lot of simulations done is kind of in your day, there's some choices to be made here that are pretty impactful.
Yeah, exactly. Mm-hmm. So there you would simply, I mean, the x-axis would not be that important, but you would simply look at what is the optimal performance that I could get, and there I would just look for the maximum on the y-axis, right? So if I would want to run ribosome simulations as fast as possible, then I would go, for example, for multiple C5N instances here that scale pretty nicely. You see they are more or less parallel to these lines of equal performance to price, and you can get quite a speed up here, for example, on 32 of these instances. So that this will give you a lot better performance than compared to any other instances, just single instance performance.
Yep. And it's interesting to note that if you have a simulation that you can scale out and is capable of scaling out, the CPUs actually are definitely much better than the GPU scaling out, right? As you can see from one of the examples over here. But from a price performance perspective, that it changes. But if relative cost weren't a feature that you're really trying to get to, I think just scaling out the workload just makes sense. And that's something that is now possible with the cloud as well, which allows you to actually gain access to multiple C5N instances, which are possibly not the case if you have an on-prem infrastructure, for example.
Yeah, so the nice network is the key to good performance here for the C5 instances. That's true.
This is where we can say something nice about Elastic Fabric Adapter, EFA.
Yeah, you immediately see the difference, right? So you could also scale out on the G40N nodes, which are cheaper, but they lack the EFA adapter. So at some point, the performance will just drop below the C5 curve. So if you really want to do scaling as much as possible, then you need to take the instances with the best network.
Correct. Exactly.
Right.
Yep.
They do quite well until a certain point, right? And when they cross the black line. So
yeah, although you do see that right away from if you're going from 1 to 2 C5 instances, you don't lose much parallel efficiency. You're nearly at 100% parallel efficiency, while for the slightly slower network, you see a decrease in parallel efficiency.
Right. And that's really, in many respects, that's just Amdahl's law. Kicking in a bit earlier. Yeah, okay, that makes sense.
Mm-hmm. Yeah, exactly.
So how do we, when we're comparing CPUs to GPUs, I mean, that's interesting. What about, you've got some data, I was just scanning, right. There's some data there about, comparing the different CPU classes, the different CPU, the processor makers between each other and GPUs as well. Is there an insight to be gained out of that?
Well, are you referring to this diagram or to
the
general?
one on the bottom right, the table on the bottom.
Okay, I see. Yeah. So, this is a project that we want to do, where it's not so much about scaling out one single performance to as many instances as we can get. So we don't necessarily want to maximize the single simulation performance. So here we are looking at
zoom in a bunch.
A bunch of sims. Yeah,
No,
so these are.
Can you?
Oh,
zoom
I'm
in
sorry.
more?
Yeah, I see. Okay.
Yeah, thanks.
Yeah. Okay, now you see something, right?
Yeah, that's it. Oh, look, there's the numbers there.
Yeah.
Okay.
So this is a whole simulation project, and this is made up of about 20,000 simulations, and we want to get down with the time to solution for this project as a whole as much as possible, right? There we would what we've done is we've benchmarked different systems, so different individual items of this whole simulation ensemble on all of the or of many of the available instances, and then we can look at how long does it take for this simulation to complete on different instances. So to read that, I mean, this 100,000 atom system here would take about 50 hours on a C5 to XL machine. And if you would do that on demand, then you would have to pay about $17 for that. And you can go faster and faster by choosing better machines, although that would also come at a price, that's true. But if we want to optimize the whole thing for performance, then we have to look at the best performance that we can get from a single simulation. So this is the largest simulation, and we could go down to 6 hours for that on a P4D. So this would be our time to solution. And now we have to take care that all the other members of our simulation ensemble should not take longer than these 6.1 hours. And but there we can now optimize for price, right? I mean, we don't need to do all the simulations on the most expensive, on the most powerful instances. We could easily, with the smaller systems, go to let's say C5 9XL or so. We are still finished in less than 6 hours, but it's going to be at a much reduced pricing. So we can optimize both time to solution for our whole simulation performance and the price tag on the whole thing.
And that's where we really utilize the cloud to the fullest, right? On your internal system that takes, what was it, like 3 days on 500 nodes?
Yeah, but this is already if we have the cluster exclusively for us, which is normally not the case. Exactly. And here, this is the thing that you could do only in the cloud. We can really start all the 20,000 simulations at once. At least that's the plan what we want to do.
Yeah, we want to run it globally, right? We want to utilize AWS Batch and run it on a global scale. And we looked at the biggest systems to define the wall clock time that we have. And all the smaller systems, they can run for as long as the long system needs to finish. And this 6 hours would be the most aggressive one, right? If we would dial it to like 12 hours, let's say, we can, of course, tune this to have a better price performance, right? Or if we say we start on a Friday and we want to finish on Monday, then we can even optimize this to the fullest, and we can. But we want to be aggressive with our run, and we want to finish as fast as possible just to show what's possible.
Then you guys just signed yourself up for coming back and talking about that.
Yeah, sure.
And writing a blog post about it and writing a workshop on it so that everybody can download the workshop and do it themselves. So we're more or less at time. Has anybody got any last thoughts that they want to get out? Austin, I'll pick you first.
Yeah. So one of the things that I'd probably iterate over here again is that I think different systems have different exhibit different complexities. And I think a process of benchmarking is always good. From the last diagram that Carsten showed, I see that the price performance for these three systems are different, and some are better on GPU and some are actually better on CPU. And this is something that I see. That's something that you can test on the cloud very easily to arrive at the right system for you, which you can then continue to use in production runs, basically. And that's something that you can automate as well. Yeah, just wanted to bring that up.
Carsten, any last thoughts?
Yeah, I mean, I can just concur what Austin says. So that was also a nice thing for me to see, that you can just pick from all the instances that you guys offer, just the one that is best for the job, and that I liked a lot.
Exactly. Yeah.
And Christian?
Maybe one, yeah, I think we need to do a shout out to the spec team as well, because we are using spec to install GROMACS here in different variants, right? I think that's the first one that we missed so far.
And spec is one of the greatest things to happen to HPC software.
Thanks, Todd.
Makes life so much easier.
And another one, I think that through this project, what really amazed me was this left-hand top plot, because it makes very clear that we have so much diverse instances, and it's really worth looking into all of those instances. And I think the G40N, I wouldn't say came as a surprise, but somehow we tested it, or you tested it, Carsten, and you said, I have something nice for you on Friday. And I was like, okay, what's going on? And the other thing is the right-hand plot also that shows that you should pick the instance that is right for the job and has the right price performance, right? So I think that's pretty amazing.
That is a really nice place to finish. I've been building HPC clusters for a couple of decades for customers, building them out of hardware, building them out of cloud now, in the last few years. And almost every interaction with a customer who's building a large centralized HPC facility is they would optimize in this kind of challenge with this set of customers, along with no doubt several other different types of end users. They would absolutely optimize for the fastest GPU with the fastest network, with the most CPU cores, the most memory. They would maximize every single node in terms of every single technical aspect of performance in order to get, simply the fastest machine that had no barriers inside it. It would cost an absolute ton of money to build, but you could run virtually any code on there. The lesson out of this is optimizing the platform to fit with your code gives you a very different result, because the first case would end up with a customer building something very similar to a P40N. And what Carsten's data here is showing is that's not optimal for either of the scenarios that he was looking at. Either fastest wall clock time or fastest best price performance. Both metrics, he came up with a very different answer to that. Everybody, thanks for coming. Carsten, especially, thanks for doing all of this work.
Thanks for having me.